Hey, so this week we're going to talk about gradient descent. So I know that a bunch of you do not have a lot of deep math background, and I know that I really can't get into sort of the deep, multivariable calculus of the math behind neural networks, much as I might like to try. But we kind of need to have some intuitive understanding of what a gradient is and what we're trying to do here in order for some of the later content to make sense. So an example is a thing called the rectified linear unit. Some of you may already have heard of these, right? Rectified linear units have replaced sigmoids, and we'll talk about this, in a lot of areas. And in order to understand why that they work better, you have to understand what a gradient is, right? You have to kind of be able to look at each of these functions and see what the gradient of each one is and understand why that's going to make one of them train much better than the other, right? So in the upcoming slides, I'm going to kind of shoot for an intuitive understanding, right? I'm not really going to do a lot of math derivations. I'm not going to make us understand how the math actually plays out, but I do want to get an intuitive understanding of what the gradient is and what role it's going to play and why the derivatives of these functions are going to end up mattering, right? And I should say, I suppose, let me know how well that works, right? So a good thing to talk about on Tuesday or Thursday is the pacing of these slides, if you are completely lost, if we need to go over this more, if I need to factor more of the math out. If you find the low math level in these slides unsatisfactory, then you can also talk to me about that during the question and answer section, or in email, because my West Georgia email should be getting set up fairly soon. And I can point you at some more mathematically satisfying resources, right? But right now, my main concern is not leaving people behind who don't have a math background and don't want to mess with it, right? Okay, so motivation. Let's say that we wanted to decide if the user had clicked inside of a button. That's a fairly easy problem. This button has so every pixel in this button has an XY coordinate with respect to the screen. And all we need to do in that case is figure out if the XY point of the user's cursor is inside of the button when they click. That's a fairly easy problem, right? There is, a fairly straightforward mathematical definition and solution to what we're trying to do. Let's say that we want to decide if this sound file contains a flute. That's trickier, right? So looking at this, is that a voice? Is it an instrument? If it's an instrument, is it a flute? If it's a voice, is it, a speaking voice, or is it like a singing voice in music, right? That might also have a flute in there that we want to pick out. This is kind of tricky. So we still have techniques that we could use to do this, right? We have the good old Fourier transform. We can start looking at frequency domain stuff, right? We can start talking about convolution filters. It has been years since I had this class. I probably could not do this right now if you put a gun to my head. But in principle, sort of DSP people, digital signal processing people, can talk about ways that you can start to address this problem. It's a harder problem, but it's still doable. But what if we want to decide if an image contains a face? That's tough, right? So the face might be in different places in the image. Like it might have a different angle. It might have a different size because it's closer or further from the camera, right? So it might be in sort of profile, right? It might have shading on one side, which would make it easier to pick out features like the nose, or it might not, right? The eyes might be closed or open. There's all kind of things that are going to make that much harder to do, right? It would be very hard for me to describe to you a sort of explicit algorithm, right, in terms of 4, pixel in image, do something that could find that face, it might be impossible, right? I might have no idea how to write that program. Well, what if we had a universal function approximator, by which I mean a machine, and here I'm using machine in the same sense of like Turing machine, an abstract logical machine. This behavior, so that approximated functions obviously, and this behavior was controlled by a set of parameters theta. Then we could solve any problem, including potentially our hard face problem, by formulating it as a function approximation problem, and then just finding good theta, if we have a way to do that. So basically, write our problem as function approximation, and then tune our theta until we get it. Right? Advance. So for the next few slides, I am going to use approximator and model somewhat interchangeably. By both of those, I mean this thing. I mean the bespoke universal feature approximator. Draw a better circle. There we go. That we are training to solve our problem, right? That is our model, that is our approximator, that is our learning agent. Also worth noting is that finding a good theta can turn out to be surprisingly tricky, right? So the way that I have described this, it might sound like, neural networks are easy. Why is this a research area? Why was it hard? Well, so yeah, turns out finding good architectures and good theta for all of your different problems ends up being pretty tricky. All right, so formulating our problem as a function approximation problem isn't as limiting as it sounds, right? It turns out you can kind of model all of computing that way from a certain perspective. But it's useful to note that a transformation in how we think about computing is happening, right? We're moving away from a world where we're going to write code like, for patch in image, right? And I'm going to be writing an explicit algorithm that we can understand, and we're going to move to a world where we're going to start thinking about, oops, I turned off my pen. I am smart. And we're going to move to a world where we're going to start thinking about training data, right? And labels, and then training a learning agent on this data. Okay. So gradient-based training. So again, if we're talking about finding a good theta, this all sounds well and good, but do we actually have a way to efficiently find good theta? Well, we kind of do, and that is gradient-based training. So what we do with gradient-based training is we define a loss function, and this is supposed to be a Blackboard cursive L, but this font is bad, right? So we define a loss function that takes two arguments, m and d. M is the output of our model. D is the desired output. These might not seem like the most intuitive sort of letters to pick. I am doing this to follow along a sort of well-respected paper in this area that I will link later for anyone who is curious. And I want to try to follow their notation as much as I can, because it's going to make your lives much easier if you don't have to learn a whole new symbology to read a new paper. So if you read papers a lot, you are going to find out that a lot of different authors use similar symbols very differently, and it becomes really, really irritating. So I think it will be a minor service I can do you to try to stick pretty close to the sort of way that these symbols are used in some of the big deal papers, right? Not that I expect you to read those papers for this class, obviously. So anyway, given our loss function, we then compute the output m of our approximator / model, given an input x, and then we compare m to a known d, which is the desired behavior. So we have an x, we have the d that we wanted, and then we look at the m that we have, and we compute how bad the model did, right? And that's the loss function. So then, we change each little theta, each parameter, in big theta, which is the set of parameters, to reduce that loss. Okay? So what we're talking about here is we are descending, well, hold on. Right. So we are so that last step is where the gradient comes in, right? So the gradient that we're talking about is the gradient of the loss surface. So what the gradient is in sort of multivariable calculus, you have a function that maps, let's just say 2 dimensions, right, onto a height, then you can think of that like a surface. Okay? And the gradient points in the steepest direction of increase of this surface. It's a math construct that points up the slope, basically. If you think about this as the loss, so if we have a function that is producing our loss, and we think of that loss as a surface, and if the high points of that surface are where the loss is high and our machine is doing badly, and then the low parts of that surface are where the loss is low and it's doing well, then what we're hoping to do is incrementally, right, step down that loss surface. We're going to follow the negative gradient. So the gradient points up, we want to go down. So we're going to follow the negative gradient and take little steps down this loss surface. Okay? So that's what we're doing, and that's where the gradient comes in. Hence, right, gradient descent. So another little subtlety, or I should say a subtlety, is in order for the gradient to make sense, our loss function has to map 2 real vectors. This one is M, this one is D, right? Our model behavior and our desired behavior, onto one real number, which is the loss, right? It also has to be differentiable, right? Our loss function and our model, in fact, so mx theta, both of these things have to be differentiable. And they have to have a few other important properties too. So one of the most important properties that didn't make this slide but should have is L needs to tell us how well we're doing. And I think I had that in the previous slide, and I just skipped ahead of it accidentally. Yep, there it is. So a good L will have the property that when M and D are very different, right, when M and D are different, the loss is high. And then when M and D are similar, the loss is small, right? So this has to be true if L is going to define a gradient that we want to descend, right? So, in order for this goal to make sense, in order for descending this L to make sense, it has to be true that high L corresponds to bad performance and low L corresponds to good performance, right? So, like, meaningful, right, in terms of low loss being good performance, one-dimensional output, and differentiable. Do we have functions that satisfy that requirement? Well, we actually do. One of the most common is the fairly straightforward mean squared error, which we'll talk about later. There are a couple of other common losses. Not all of them make as much sense. So if I told you that we're going to use the mean squared error as our loss function, intuitively that would make sense to you. There are other loss functions that maybe intuitively don't make sense, but they end up having all three of the properties that we care about, and so they're useful. So one problem that I have heard similar classes have is that students can get a little bit confused about the difference between the set x, which is the input, and the set theta, which are the parameters. Right? Here's something that I hope is going to help. So during training, x, which is the set of inputs, are constant in wiggle quotes, and we're going to be changing theta. While the network is being used, we can kind of usually think of theta as constant in wiggle quotes, and x, the input, is the thing that's going to be changing. So here's what I mean by that. Usually in training, your input, your x, is some sample of data you've prepared to train the network, right? If you're going to train the network on faces, then x is a bunch of images of faces and not faces, right? And that's your x. This is the set in operator, if anybody hasn't seen that, right? Set in. And then if you're training a neural network, your weights and biases are the parameters in theta. While you are training, your sample set of images is probably fixed, right? You are not generating new images in the general case, and you are not generating new labels, right? So x and d are fixed. And theta is what's changing. You are tuning the weights and biases, okay? When you are using the model, when you are using it so out in the wild on unseen data, then you, hopefully, have already found some good theta, right? You've already found good weights and good biases that lead to good performance, at least on the training data. And now it's your input that is A, changing, and B, probably unseen, right? So when you're using the network, it's encountering all new data that it's never seen before, right? Oh, and notable, like both of these are sets, right? So x is a set of inputs, theta is a set of parameters. So the reason that those are in scare quotes is that that's not really always true. There are training methods where you will collect new data while you're training, so x isn't strictly constant. And there are like online learning methods where theta will change over time as you gather new data, so it's not always constant. But in sort of the basic, common, like feed-forward neural network case, we can kind of think of it this way, right? Yep. So here's kind of a little schematic of that, right? Hopefully this is going to help assemble everything. Oh no. I just glanced at OBS Studio and saw that it was recording the desktop. I really hope as I review these slides, it's been getting LibreOffice most of the time. I'm a professional, everyone. So in training, right, x is kind of dashed out because it's going to be effectively constant, right? It's not literally going to be the same every single update, but we have one set of x and d that is what we care about, right? These we already have. We're going to run over them 100 times. They're going to be the same every time. Theta, right, is what's going to be changing. So in training, we given our approximator, we use an input or set of inputs x, a set of parameters theta, we get an output m. We compare m and d, the desired behavior, model output, desired behavior, compute the loss, then we adjust our parameters to reduce our loss slightly and repeat, right? So we iteratively approach. Oh Yeah, I'm looking at a blank screen. Dang it. Okay. So in use, we're not going to bother with the loss and the parameter update, and we have now a fixed theta. Now we're looking at x unknown and computing model output for the unknown novel input, right? So in use, it's just theta is constant, we feed in unknown x, and we get model behavior for those. Yeah, it seems to screw up every time I turn the pen overlay off, which is not ideal. So again, just to try to make sure that everybody has this completely sort of squarely well understood, we're often going to look at equations like this. M might be some function of x and theta, and that function might look like this. This is sort of one feed-forward neural net later. Tan h is our nonlinearity, it's the hyperbolic tangent. W is our weight matrix, x is our input, and b is our biases. And we'll talk about this later, right? Right now, just kind of think about it symbolically. Don't worry about it. So in this scheme, w and b are our parameters, our theta, right? And little x is our input. So we're going to talk about the derivative of this. And you might immediately say, if you've had calculus, oh, I can differentiate that. Well, maybe I have to look up what the derivative of tan h is, but once I know that, I can take the derivative of this. Well, you don't actually want to get the derivative of it. I'm having cat problems. She keeps deciding her feeding time is hours earlier than it is. So you might say, I can look at this and say, oh, I can differentiate that. Well, to descend the gradient, we don't actually care about the derivative of the output with respect to x. Okay? We don't care about that. What we want is the derivative of the loss function, right? Loss of model and desired, which is loss of all of this stuff, with respect to the parameters, the w in w. So we want derivative of loss with respect to w and b. Those are the derivatives that we care about, right? Derivative of loss, partial loss over partial w. Okay? That's the gradient we want to go down, right? The loss is the gradient, the loss surface is the gradient we want to descend, and w and b are the things that we have to descend it, right? The tools we have to step down the loss surface. So we're going to write, stuff that's going to look like a good old calculus function of x. Don't be confused. The terms that we want the gradient of are the terms of, or is the derivative of the loss with respect to the w and the b, because those are the parameters, right? Those are the controlling parameters. Okay, so thought for later, how are we going to pry that d theta out of that function, right? So, I need to figure out why it's doing that, because it's real bad. So how are we going to pry? So if we want, that's supposed to be an m, my mistake. So if we want dl dw, how do we pry that out of this? Well, the chain rule. So we're going to use the good old multivariable chain rule later. And again, multivariable chain rule is not a thing I expect you to understand, right? We're not going to worry about that. We'll talk about it a little bit. We're not going to make you apply it. So some drawbacks and subtleties. We might not know how our approximator solution works, right? So I want to be kind of precise here, because some people there are different statements that are made about what this means, what we do and don't know about how our networks train. On some sense, it is perfectly well understood how gradient descent works, right? So we basically have some function that is controlled by parameters, and we're incrementally sneaking those parameters in the direction that improves our performance by reducing our loss. That is, in a certain sense, a mathematically perfectly straightforward description of what's happening. Now, you'll hear that we kind of don't know how our solution works, basically, and what people mean is we don't know the behaviors that it's learning, right? So if we have some huge model that has hundreds, thousands, millions, billions of parameters, it might be very, very difficult for us to develop abstract descriptions of the kind of behaviors it's learned, the kind of rules it's learned to solve the problem, right? We might not be able to inspect our network and talk about how it's going to behave and what it's learned to do. So on one level, gradient descent is perfectly well defined, right? But on another level, it might be very difficult for me to tell you what kind of features that our face detector has learned. And it might have strange pathological behaviors in cases I didn't anticipate that I will not be able to detect just looking at the weights, won't be able to predict, and might not be able to explain in terms of reasonable rules, right? So to some, right, we might not be able to understand the kind of behaviors our model has learned to solve the problem, and it might surprise us, and that might be bad. So our approximator might not be trainable on all problems, and an important thing to understand here is that there is a difference in compute power and learning power, right? Learnability. So it might be true that for any Turing computable function, there exists a neural network that solves that function. For any Turing computable function, there exists a neural network that approximates to arbitrarily. Okay, good lord, I'm getting tongue-tied. For any, I should not have tried to get into that without having it in front of me. So for any Turing computable function, there exists a neural network that can compute that function to arbitrary precision there, right? That could be true in principle. It might also be true that if we start with a network of a certain size and with a certain initialization and then train it under gradient descent, it might never converge to that function, right? So even though we know that good parameters exist, good weights and biases exist that solve a problem, we might have no way to find them by using gradient descent, right? That problem might not be learnable under gradient descent. Okay. So, minor edit cut for technical and cat-related issues. All right. So another problem is we need a huge amount of data, right? So if we have a complex problem, which can range from a bunch of language tasks to flashy results like playing StarCraft, then you need a very large model, right? But large models, in order to be trained well, require large data. And this introduces a bunch of practical problems, right? So data can be difficult to gather, it can be difficult to process. On a basic level, it can be difficult to work with, right? When large starts going into the terabytes, then you start to have a bunch of practical problems like, how do I handle a terabyte-sized data set if my GPU has 4 gigabytes or 8 gigabytes memory, and it has to split that between all of my model parameters and some portion of my data, right? Getting this to work can be, a specialized skill, right? It can be kind of tricky. So one of the other problems with this, right, is just gathering data, right? It might not be possible to gather a large corpus of good data. Oops. Right? So yeah, our model is only going to be as good as our data is. If our data is biased, then our model is going to be biased. If our data has holes, then our model is going to have holes. And by holes, I mean sort of unanticipated behaviors, right? If I'm training a robot that's going to be walking around in 3 dimensions, then my data has to cover, my training data has to cover every behavior I want it to have in every situation I can reasonably expect it to encounter. If it encounters a behavior that I could never have predicted, right, then I don't know what it's going to do. I haven't trained it on that behavior, right? It might behave in an intelligent way, it might go nuts, right? So bias in data is really important to consider as well, right? I have a friend of mine who talks rather glowingly about his hope that artificial intelligence can be used to replace a bunch of human tasks where judgment is required, but human judgment is known to be faulty, right? It is known to be biased, consciously or unconsciously, maliciously or not, by racism and sexism and other prejudices. Well, the problem with hoping that AI will save you there is that how do you train the AI, right? If you train it on existing, for example, jury decisions or credit decisions, and we know that those decisions are deflected by conscious or unconscious bias, then your training data is biased, and the behavior that your AI will learn is also going to be biased, right? That problem won't be fixed. So our model is only going to be good as our data, and we might need a lot of it. All right? So gathering large quantities of high-quality data is hard, right? Up to the point of sometimes being impossible, right? So sometimes you might need huge corpuses of data to train your model, right? So if you're training like social recommender algorithms on very large corpuses of like social connection graphs, if you're training large language models, if you're training large image processing and captioning models, then you are going to need huge amounts of potentially labeled data. You might not be able to gather that at all, right? Which is one among a couple of reasons that, like SciFar, we're going to talk about. SciFar is a data set, right? One reason to talk about SciFar is that it is an existing standardized corpus of labeled image data, right? And while it is important to have, so a standard data set for training, like for benchmarking like new techniques, for example, it's also just convenient to have this large corpus of already existing gathered labeled images, right? So lots of human work hour could be required, right? If you're working on an image corpus, then you have to label them, which basically means you probably have to have some human go through hundreds, thousands, millions of images and label everything in the image, right? Not every group is going to be able to do that, right? Those kind of human work hours end up being expensive, right? If you're training a speech processor, you might have the same thing, where you need some way to break long runs of recorded speech, which you only might have, into labeled units of speech, right? Little labeled snippets where you've labeled words or maybe even phonemes, and again, that's probably going to require either a lot of human work hours, right? Just people going through there and labeling frame by frame every sound, or the help of subject matter experts, right? So I looked into processing EEGs, right? Electroencephalograms, to detect various properties of the person whose EEG it was. One of the tricks is you really need the help of psychiatrists to process that data, right? Raw EEGs are difficult, and you need the help of subject matter experts in experimental psychology to intelligently pre-process those EEGs, right? So you might need lots of human work hours, you might need the help of expensive subject matter experts, and it just might not even be possible, right? It might not be practical to gather a large corpus of data at the quality that you need with correct labels, right? That might be difficult to the point of being a practical impossibility. All right, so a final little thing. Let us train a line by gradient descent. So, again, that should be L. So I'm going to use the mean squared error, which is this. Don't worry about it. So notice that basically it's supposed to be a 1/2 there. Whoopsie. So true to the name, we compute the error, right? The difference between, and that's supposed to be an m. I did good on this slide. So it computes the difference in the model output and the desired behavior, right? And then it squares it. So it's squared error. And then it sums it and divides by the number of samples to get the mean, right? So exactly as it says, mean squared error, right? And the model I'm training is not a neural network with a bunch of weights and biases. It is a line, right? This is a scalar. This is a scalar. It has two parameters, m, which is a real number, and b, which is a real number. This is the slope. This is the offset, right? We remember, like, y equals mx plus b is the equation for a line. So let me see if I can quickly launch us a spider environment. And too many tabs open. You know what? I'm going to be pseudo-professional and just pause the video and I'll get back to you. All right, here we go. So, hello there. So this is sort of TensorFlow code. We're not going to look much. We're not going to get into this very much because this is not really typical of the kind of TensorFlow code that we're going to be writing later. But you can see my, so if you will, my model here, which is just the equation for a line. You can see that I've got two variables, right, which I'm declaring as a tf.variable. They're used in the equation for a line. Oops, what? Stop it. All right, I have outfoxed myself here. Okay. So I'm declaring tf.variable, and again, this is not typical of the code that we're going to be using, so I don't want to go over it very much. Reminding myself as much as anything else. So I've got my line equation, I've got my loss function. My loss function is, so reduce mean just means average, right? So it's 1 over n, sum of the thing inside the reduce mean, which is y minus d squared. And again, that's supposed to be an m. I'm dumb, right? So it is 1 over n sum of model minus desired. That's mean squared error, right? My loss here is the mean squared error. I'm picking 2 sample points. We're not going to worry about that too super much. And then I've got a training loop down here where I just compute my output, right? Get my output, compute my error, get the gradient, and then step down learning rate times derivative. That's the update. So it's learning rate times update. Again, we're not going to worry about that right now. And then the other little thing that I do, which will matter somewhat later, without getting into it too much, is I am going to plot an image. So I'm going to store what m and b were at each step, and then I'm going to plot an image and save it that is the line I've trained, right, the line that's in the model, and the desired line. And we're going to get to actually watch it approach. So this model is not large. And if we click run, there is what m and b is at each step. This third column is the loss. Notice that it is like times 10 to the negative 11. So that's scientific notation, right? So it's some number, right? So some number times 10 to the negative 11, which is to say the loss becomes tiny, right? That's a tiny, tiny little loss. And if we scroll up, 6, 5, here we go. So fairly early on, right, the loss decreases steadily. In the very first step, it goes from 8. That's not 8 to the negative anything. It's just 8. It's a fairly big loss. Stop it. The reason it jumped down to the bottom was it finished saving all the images. So it trains, then it saves all the images. But in the very... Oh, we lost our history. In the very, very first step, right, the loss is large. But then it immediately went from 8 to 3, and then the 3s stepped down fairly rapidly, right? We see a fairly steady decrease. We get to less than a whole number. We get to 2 leading zeros, and it just goes down, down, down. Right? So, I'm going to use the Unix utility ffmpeg, which I have written down a reminder of what that command is. That's a comment, right? So it begins with the hash character, so it's a comment. It is me reminding myself what the magic ffmpeg command is to render all of this, because there's no way I'm going to remember what the format of all these options are. ffmpeg is a thing for processing media. It has a jillion options. I'm not going to remember it all the time. So, I now have off screen, just so you can see it. There we go. There's an example we'll get to later. But there we go. There is all of our frames that were saved. So let's look at frame 1. Haha, there we go. There's where our line started. That's frame 1. Frame 2. Let's see frame 20. 20. Okay. So let me run that ffmpeg command. Yep. And now it has made that video. And now if we ff play, .mp4, it shows up on the wrong monitor. Let's try that again. All right, it's not going to stop showing up on the wrong monitor. Do I have VLC installed? No, I don't. The hazards of doing it live. You can't see it, but I'm opening. There it is. Okay. All right, sorry everybody. So, here is our line. And Totem has crashed. Good job, Totem. Totem is the GNOME media player. All right, here we go. We're now, I think, please God, on frame 1. There we go. Isn't that neat? So you can see it starts out fairly wrong because we initialized W and B randomly, and the odds that a random weight initialization are going to be anything close to right are pretty low, right? But it shoots up real fast, right? So in the first couple of frames, you can very quickly see the line shoot up vertically until the center of the line hits the red line. That's the target. The red one is the target. So what you're seeing there is that B term training. And it gets the B right pretty fast. See that? Shoots up real quick. And it gets B right pretty quick, and then it tunes W. And you can also see that the larger the weight update is, right? I'm sorry. So you can see the larger that the error is, the larger the training signal is going to be, right? So early on, when it's wrong a lot, it turns fairly quickly. It tunes that slope fairly rapidly. But as the slope approaches the target, the error becomes tiny, and the training signal becomes tiny correspondingly, right? So it kind of shoots up very quickly, and then it turns very quickly, and then slowly, until it's very, very close and it's moving very slowly, right? So it's kind of asymptotically approaching correct, right? But it does keep very, very slowly creeping toward the correct answer, as you can see. And it eventually gets, well, fairly quickly, gets imperceptibly close, right? So this is the point where it's still off by a little, but it's off by, you know, something times 10 to the negative 11, right? The error is small enough that we don't actually care for any real application. So you don't need to understand this TensorFlow code, because we're not really going to talk about, we might talk about code like this if we decide to talk about writing custom models, which if you all decide you want to by vote, we will, but you don't really need to understand it in depth. You do need to understand what it did, right? So here, we didn't train, this is not like a big, complicated, like tan H wx plus b, right? This is not a neural net, right? Where this is what a neural net is going to end up looking like. This is just a little like y equals mx plus b line. But understanding how we trained this line and how it's behaving and what it did is going to be convenient for us later, because we might use something like this as a sort of simple context for talking about some of these other issues, right? Okay, so yeah, that is a short overview of gradient descent. This video is gradient descent applied to a line. Hopefully, ideally, that's gonna be a good intuitive discussion. A good intuitive discussion without being mathematically overwhelming for people who haven't had calculus. Now, I'm going to say. Also, my timer indicates this is probably going to be around 30 to 45 minutes. I feel like that's way too fast for this material, so I am going to be wanting to hear from you on Tuesday, assuming that the stars align and everything works well and we're all in class like we're supposed to be. I'm going to need feedback from you if this was way too quick, way too slow, didn't make any sense. Like, My mission, right, is for y'all to understand all of this pretty well at the end of the semester, right? I need feedback from y'all about how this is going. So if we were in a class environment, I'd be able to look at you and see. We're not in a class environment, so, or we're not right now. I'm not right now as I record this. I will be on Tuesday, so I'm going to need that kind of feedback on how we're doing, right? We doing okay? We lost? All right. Yeah, so see everybody on Tuesday, hopefully.